All right, important updates. I just released the solution to your assignment number 1 just about 5 minutes before the class. So please check. If you go to the E-class, you will see 2 things over there. So for assignment 1 solution. So there's a Java code simply containing the solution to all the recursive method. Okay, so you will see solution code. If you kind of feel very confident about the 4 problems that we kind of solve in assignment number 1, you can feel free to go ahead and look at the solution to see if there's anything that might interest you or surprise you. You can discuss with me. But if you don't really feel that comfortable with solving any of the tasks, for assignment number 1, I do have some video walkthrough to really kind of walk you through the solution. So there's also a PDF where you can find links to some videos. I think for every one of the 4 tasks, you can see the solution walkthrough. So they were actually drawn from some previous review session I did for 2101, your fellow students. So you can definitely check out these 2 resources. And then next week, I'll try to release your programming test number 1 guide just earlier. So you can definitely get clear about the expectation for the test. And I'll give you guys some example questions to practice. All right? But just don't forget, practice question is only for example. You really have to do a little bit more, on your own as well. But if you want to discuss any general strategy about preparing for the test, if the guide is still not enough for you, you can definitely reach out to me, right? So I'll always be ready during the office hour. We'll speak to you after class. And don't forget to also go over this hybrid sorting algorithm, combining selection sort, insertion sort. That one there is not really necessary for programming test 1, but for your written test, it's definitely covered, right? Just make sure you kind of don't overlook it. Your assignment number 2, which will be based on linked list. So today we're going to program maybe 1 or 2, at least 1 or 2 methods just to get some feel. But I think assignment number 2 itself is going to be more challenging, of course, than the actual lecture material. But you got all the basics, right? We kind of went through some visual operation last time, so you definitely got enough idea to get started. So you will get 2 weeks to actually do it. But of course, the sooner the better. Okay. Any questions? All right, so the plan will be today we're going to do singly linked list, dive into more methods. And also most of next Tuesday, we are also going to somehow hopefully finish off most of the methods in singly linked list. And in the last lecture before the reading week, next Thursday, I would like to touch upon a little bit about doubly linked list. It's just some slight extension to singly linked list. For some of the operations, we can somehow improve the performance, but for most of them, it will remain the same, right? That's kind of something you want to keep in mind as well. Okay, well, we'll get there. That's kind of the plan before the reading week. Okay, but after the reading week, we're going to start very excitingly about trees. It's really a big topic. I'm excited about that topic there. Right, we'll discuss. All right, if no questions, why don't we do a very quick recap, and then we'll dive in to linked list. So we had some gentle introduction about the critical points about singly linked list. Just remember, reference aliasing is so important, especially in Java. You want to know the way we kind of use the next operator is really try to use the references, right? And very often, to really get to a particular node in the chain, you may have more than 1 possible ways to really get there. For example, to really get to this particular node, you can either say, oh, it might be the tail. That's 1 possibility. Or you can say it is this particular node, let's say node 1, dot next. That's another way. Or you can say this is node 0 dot next. So you got multiple ways to really get to a particular position in the node. That's really reference aliasing. That's something I assume you guys know about from 2030. And then we'll talk about a linear collection. For now, just remember every node in the linked list has a unique successor by following the next reference. Successor will be whatever node that comes after it. And we spoke about absolute versus relative positioning. So for array, when you try to do indexing, it's all about calculating the corresponding memory address and get there. Very efficient operation, just constant. On the other hand, for linked list, you simply have no idea how many nodes might be stored at the runtime. It could be arbitrary. The length of the linked list is only bounded by the memory you have in your computer. In today's world, of course, memory, you can almost think that is almost unlimited. So you don't need to worry about like a storage, any issue about storage. All right, so relative positioning is always starting from the head and then somehow want to get to a particular position in the node. That's something we might see today or maybe next Tuesday. So this operation here is fundamentally inefficient for linked list because you got to follow that many next references. Okay, so it's going to be linear time, right? So that's something we kind of look ahead, but we're going to see some Java code to really get ourselves convinced. All right, so this page here is actually very important. Before last winter, I kind of usually try to go over Java code and do this one last, like a visual summary. But last winter and this semester, I kind of decided that let's have some visual introduction, summary right away about the different critical operations. I would say this one here is really important, so make sure you review about the various insertion, removal operations before your assignment number 2. It's going to help, right? Just to see what should be involved when you try to set the references and when you try to visualize what's going on, right? It's so important. Do you guys have any questions about any of the operations here? You want me to repeat? All right, hopefully that's clear, right? Okay. I would say for many of the mini steps that you have to apply for your assignment number 2, it will fall into one of these somehow, right? That's something you want to keep in mind, okay? And then we talk about Java code. So for now, we make this assumption that the node, individual node, always stores string. But we're going to make it more general a little bit later, okay, just by making the class generic. Okay. So for now, we assume it's going to be string value. And then at the top level, we have another class called singly linked list. That's something I will recap as well. It's a quick examples today. Right? So it's important to set the head to be the beginning of the chain right here, right? The head. Okay, so there are 2 classes here you have to worry about. One is the top level singly linked list, which has only the head. And the other one will be a chain of node objects, as many as necessary. One thing, again as a look ahead, we start with by assuming there's only one attribute called a head. But later on, we're going to see that there will be more like a trade-off between time and space. We can potentially choose to extend the structure of the singly linked list by 2 more attributes. One will be for tail, the other one will be for the size. But that's something I'm going to discuss a little bit later. But for now, let's assume we don't have those attributes, in which case, if you want to get to the tail, like at the end of the chain, or if you actually want to get to count how many nodes you have as a size, we got to do it, right? That's something I want to go over first before we talk about the trade-off. Okay. Sorry, let me just plug it in. Sorry for the delay. Okay. Okay, so that's about the 2 classes. And then we talk about how you can construct a chain of nodes, right? You can follow the approach number 1 and also approach number 2 as well, right? For these 2 approaches, maybe I wouldn't repeat. You guys can review and let me know if you got any questions, okay? And then we talk about like one single line of the chain of node construction, right? You can definitely use anonymous objects, a single line. That's something I'll definitely expect you guys to know when you want to take the test later, okay? So, but just apply that in your assignment whenever possible. Any questions about anonymous objects, right? Okay. All right, so that's about Tuesday's lecture. So let's now continue. I want to start very quickly with just talking about once you get a chain of nodes, approach 1, approach 2, doesn't matter. Once you got a chain, how you can set up a singly linked list, which is trivial. You just set a head. Okay, let's talk about it quickly. Okay, so let's say you go with approach number 1. So you already created 3 nodes. And we try to set up the next references as we try to create the node objects right here, right? That's approach number 1. And then we got Alan, Mark, and Tom. Let's say this has been set up already. So let's now we want to build a linked list. So what we do is, first of all, I want to create a new singly linked list objects, like empty list basically, where the head is simply null. So what I will do is I'm going to create a list pointing to a different kind of objects. It's not null anymore. It's simply a singly linked list. Singly linked list. And the only attribute we're expecting to have is head for now. So the head to start with is pointing to just null. Right? That's the first line. The second line, we are trying to say the list that set the head to be Alan. So what this will do is it's going to call the setHead method right here. And then this one here is going to have Alan. So the head is going to point to wherever Alan is pointing to. And Alan is pointing to this node right here. So that means the head, rather than pointing to here, is now going to point to right here. This way, we have set up singly linked list. Set up the chain first, and then you can set a head. That's one way to go. Okay? Questions about this one here? The next one is basically the same. Okay? So what I will do is similar. Okay? The only difference is this part here, we are following approach number 2 to create a chain of nodes where the constructor does not pass any next references. We simply set the next references in the following 2 lines, right? That's approach 2 we spoke about on Tuesday. And apart from that, it will be done the same way. So you can simply do this one here, which I'll do quickly. Okay. So it's going to be the list pointing to a singly linked list objects. So this part is really identical. So has the head. Null to begin with. And the next line is going to set the head to be Alan, right? Similar argument. So rather than pointing to here, it's going to point to wherever Alan is pointing to. We set it up as well. Okay. So 2 things I want to point out. Number 1. So let's say we want to reset the singly linked list. How can we do it? Reset the list. At the moment, you can see the singly linked list is pointing to this chain of 1, 2, and 3 nodes. What if I say I want the singly linked list now to become containing no chain of nodes, basically 0? Just take this out. So the way to do it is you will simply say the list dot set the head to be null. So what that will do is simply just going to say, rather than pointing to here, it's now pointing to null again. That's how we reset. Of course, the chain of null over there, somehow it will be garbage collected at some point, right? If it has nothing else pointing to it. That's point number 1. And point number 2. You want to be careful whenever you try to set a head. You really want to be sure you know what you're doing. Okay? For example, let's try the following line of code. If I say list dot set head, I'm supposed to pass Alan. But what if I forgot or somehow make a mistake? I thought Tom should be the head. Will this line compile? Compilation. Would it compile? Yes? Yeah? Because I'm still passing a node, right? So this one here compiles, but it's more like a logical error. Because what that will do is it's going to set a head to be Tom. So rather than pointing to null, it's now going to point to just right here. And what's really wrong about this, right? Let's now be a bit more careful here. So what we're doing here is, you can think about the next reference is directly pointing to just this node right here. And if we try to say this is the head, so what will be the size of this particular list? It will just be 1, because it's pointing to just right here. And that one there going to the next will just be null. There's only 1 node, but that's wrong answer. And there's no way for you to also go back to the previous node. There's no previous reference for singly linked list, right? But this line compiles, right? Be careful. So the head is not the beginning of the chain. So this will be a very subtle mistake. So I would say you want to be careful if it does happen. So that means somehow when you want to calculate, for example, the size of the list, it's going to be 1 instead of 3. In that way, you have to use the debugger, breakpoint, etc. to find out what's going on. Right? Just keep that in mind. Right? Whenever you want to set a head or set any reference, always be sure what's going on. But the best way I would suggest as a beginner will be to visualize what's happening. Maybe draw some diagram on a piece of paper. That's definitely going to help. Okay? Questions? All right, so this is more like trying to warm up from before. Okay, so what we'll do now is we'll try to look at some method. All right, right here. Hey, Amir. Hello. Hello. Sorry, guys. If you don't mind, can you please take off your headphone? I appreciate that. Thank you. Sorry about that. All right, let's now take a look at some method here. Okay, that's something we just spoke about. And the first one, let's say we don't have the tail and we don't have the size attributes in the list, but now we want to somehow calculate how many nodes are there in the chain of nodes, right? Let's see how exactly you can do that. So given a singly linked list, we want to know how many nodes are there, okay? And there will be some hints. Well, this hint is kind of the property we said earlier. You basically want to start with the head. Write a loop to go as many iterations as you needed until you reach the last node. And the last node, that next, should be equal to null. That'll be more like a terminating condition for your loop. And of course, as you try to go with the iterations, you also have to keep an integer counter to see how many nodes you have walked through so far, and then return that integer counter eventually. Right? So that's kind of the idea. And we're just going to take a look at this one here. Right? You do have some Java code on the slides, but I'm just going to go over this one. This is more like your very first method for linked list. So let's go with that very thoroughly, and then talk about runtime as well. Okay, this one here. All right, let's say this is an example list we have. We already set a head to be Alan, Mark, and Tom, right? So size should be 3. It should be. Okay. So let's now go over the code. Just to start with, this method here is going to be defined in the context of a singly linked list class. Okay. So this is a singly linked list method. Of course, we got head. That's available to us. Okay. The initialization stage, we try to initialize a counter, and then we also try to have a node called current. This current reference here is very common whenever you want to kind of iterate through some singly linked list or doubly linked list. Think about current is more like a loop counter in some way. It's not really integer value, but it's a reference for you. So the idea will be as soon as the current somehow getting very close to the very last node, well, exactly the last node. In that way, current.next will be just equal to null. You will know that it's the condition for us to terminate from the loop, right? You will see, okay? So let me write it down here. It's a little bit like a loop counter, okay, conceptually, for you to kind of measure the progress for the loop. Like the loop counter. Okay, and then like loop counter. So somehow it's actually for measuring progress. All right, conceptually. Let's see what these two lines will do, and then we'll go for the rest that's in the loop. So we basically say there's a counter there called size, and initialized to be 0 over here. And then we also have the currents is pointing to wherever head is pointing to. Okay, so let's be careful here. So this variable assignment here is saying current is pointing to wherever the current head is pointing to. We're creating aliasing, alias. Very important first step. And the idea is the current is actually going to gradually move towards the right. It's almost like an I++ that you will normally see in an integer loop. So the current right now is pointing to Alan. Okay. So what I will do is let's also trace alongside in the table as well. So we got the current is actually pointing to the Alan node. Okay. And then the loop condition here, we're using a while loop. Okay. I think you might see maybe a while loop more common than for loop for linked list, especially for the basic operation. Usually just use a current to see whether I'll get to the null, rather than saying how many iterations exactly I need to run. You will see some example there, but you gotta judge. Okay. Let's now pay attention to this condition here. Okay, I'm gonna highlight it right here. Current not equal to null. Let's recall the very basic. When you have a Boolean condition there inside a while loop, I'm saying that as long as this condition is true, I'm going to keep executing the body of the loop for iterations. Let's think a little bit more the opposite side. What does it really mean when the while loop exit? That would mean this condition here should be false. Right? Agree? Okay, let's write down that very important observation. Okay, let's write it down. So that one there is going to be as soon as current not equal to null, evaluate to false, i.e. current is equal to null. Exit from the loop. So very important observation, right? Just make sure you're convinced. Okay. And then we got two lines in each iteration to be executed. We're basically saying current should be assigned to a new reference. That reference will just be current.next. It's almost like an I++, really. And then after that, we also got to increment the counter as well. Okay? And then after the loop has been terminated, we're just going to return what's the size counter so far. Right? It's a very simple lines of code to really code up this size method. Any questions so far? Just about what's going on, right? For the code, right? So what we should do now is to trace very carefully. Okay? Let's try that. So when the current is actually Alan, right here. So Alan not equal to null should be true. So that means we should really execute a loop for the very first iteration. And then that one there is going to say, for the first iteration, let me just put another color here. So we're going to execute these two lines. All right. So the first line here, current, rather than pointing to this position, it is going to point to current.getNext. So it's going to be whatever it is dot next, which is here. That will be the node. So we're going to reassign current to right here. We're basically just moving the current to the right by one position. Of course, you can be creative. Maybe sometimes you just want to maybe move two positions. You can say current equals current.getNext.getNext. It's more like I equals I plus 2, right? Depending on what exactly you need. Okay. So at the end of the, and then we got to increment the counter, right? Which means from 0 to 1. So what does that mean? That means so far we have finished processing one node, and now we're ready for the next one. Okay. So end of the iteration, the current is pointing to mark, and the size value has been incremented from 0 to 1. I try to use the colors carefully so you can see exactly. The green one has been just initialization, and the pink one is what happened after the first iteration, right? And let's now try to say, after the first iteration, we'll go back and check this loop condition again. So at the moment, the current is actually mark. And then we'll check for this condition right here. And we say mark not equal to null. Indeed, mark object here exists. So that should be true. So we're going to execute a loop for the second time. 5 and 6. Right? That one there, first of all, is going to move the current to current.next. So basically move that to the right by one position. Right? So that will do, so current will be pointing to right here. So that will be current. So after the execution, we have current has now been moved to Tom. And the counter will be incremented from 1 to 2, right? Plus, plus, don't forget, right? It's very important. Okay, to 2. All right, we're not there yet, just yet. So the current is now pointing to Tom. Are we going to have another iteration? It seems like we're going to, right? Because if you try to evaluate, let's use one more color here. If you try to actually evaluate this condition one more time, so you basically got Tom not equal to null is also true. That means one more node to process. That one there is going to execute line 5 and line 6 one more time. Okay. That one there is going to say current assigned to current.next, which is null. That means current is now going to point to just null. Okay. So current will be exactly equal to null. Okay. You can think about current just null. You can think about conceptually that really means no more node to really get processed. So we're done. At the same time, line number 6 is going to increment the counter from 2 to 3. Okay, right here. But execution-wise, we're still going to go back and check to see if the while loop condition is true, right? And so now current is actually null. So null not equal to null, false. Agree? False. So this will mean exit from the loop. Exit from the loop. So when we exit from the loop, and then we simply return the current value for the size, which is 3. Okay? That's what we have. That's a complete tracing. Okay? Only we got 3 nodes. But the most important thing is to see, number 1, we have a current reference, almost like a loop counter. It's going to move gradually towards the right end of the chain. At the same time, after every iteration, we have to increment the counter so we can eventually return that value. Okay. Now the question is, what's the running time for this algorithm, right? The running time is really going to depend on how many times we really execute the next reference. Okay, let me use maybe a different color here. Right here. You can think about the running time depends on the number of times next reference is lookup. Okay? So you can see that when we go from Alan to Mark, from Mark to Tom, and then eventually from Tom to null. Right? In this way, you can think about 1 and 2 and 3, which correspond to exactly, we got 1 and 2 and 3, 3 nodes. So, n. Okay. So the running time will be, the runtime will just be exactly big O of n. So this is another way, if you want to think about, well, just a little bit, make it a little bit fancier. Right? Remember the little interval that we did earlier. You can think about here, the first node index 0. So here index 1, and then index 2, right? You got to kind of have that. So as soon as after, when we get to this node here, you're just going to go for the next, the final next reference and get to null. So let me just write it down here. You can think about, we got, so in terms of the index, we go from index 0 all the way to index 2. Okay? Every position there will require some next reference to see if that will satisfy the loop condition. And that one there, we know the size of this interval is 2 minus 0 plus 1, which will be 3. That corresponds to exactly how many next references we have to use, right? That's something you can also give a try. So just remember the very last reference lookup has the result null. Because as soon as we get to null, we know that we should terminate the loop, right? That's really like an upper bound for how many times you have to look up the next reference, okay? Any questions about this? Yes?
Wouldn't it be better to have a counter that increments every time you add a new node, or is this?
Are you more suggesting, sorry, say it again. You're saying the counter here?
No. Instead of having a loop that loops
Uh-huh.
every time.
Oh, I see what you mean. Yeah, it's very good. So what you're suggesting is, why don't we have an attributes at a singly linked list level? And every time if you want to, okay, let me get to there. That's a very good question. So your fellow student was asking, would it be possible not to really just use a loop to find out the get size, which will take linear time every time? Can we just have an attribute? Yes, but it will come with a price, which I will explain. Right? So that's something very good. Okay. All right, so this is one. And then I want to talk about the second method also very quickly. But that one there, we don't do any detailed tracing. I can leave as exercise for you. I will talk about that space versus time trade-off maybe after the break. Okay. So that'll be counting right here. Let's do this one before the break. Okay. Let's say if this one is very similar, but slightly different, very similar. Let's say we not really like we don't want to return just a size, integer. We want to see what's the tail, the last node in the chain. Let's say we don't have any tail reference in the singly linked list. Okay. So for example, okay, you can see Java code exact here, but let's now take a look at here, right here. So in this case, for example, let's say given this particular example list, okay, if I say something like list.getTail, okay, I'm calling this method here. In this case, it should return back to me just Tom. Okay. But let's see how exactly this one can be calculated. So this one kind of shows to you, rather than keeping some integer counter, I'm keeping some node reference, which has to move as we try to move the current. Right? So there's a little bit more variety for you to consider. Okay. Yeah, exactly. When you say list.getTail, it's going to give you Tom in this case. Okay. I want to highlight the code, first of all, just to show to you about two references we are trying to keep track. Okay. One is about the current, which we know about from before. So let's say we got the current over here. And also we check to see if the current is not equal to null. And also move the current always to the right. That's something we're familiar. But we have another, like a second reference to keep track, which is the result tail that we want to return. So this is where we define the tail to be null in the beginning. And then we also want to say tail will be assigned to the current before current gets updated to the right. All right. And eventually, we just want to return the tail. Eventually. Okay. Let me write down some observation or insight right away, so you will get the essence. But I'm going to give you some visual clarification quickly. Okay. So what we have over here is the current and tail. So very important observation. The current is always one position ahead of the tail reference. We'll see exactly. So the current versus the tail. Okay. Let's see the initialization. After these two lines right here, current is pointing to the head, like before. So this is the current. Pointing to, you can think about this like index 0, for example. Think about we got index 0, index 1, index 2, and then before index 0, it's more like index -1 conceptually, right? And then we have the tail is just pointing to null. You can think about this more like an index -1. So it's like a 0 is a 1 position ahead of -1, right? The current. After the first iteration, current right now is not null, so we should go on and set this. So the first iteration, we're going to say tau is going to be current. So tau is going to point to wherever current is pointing to. And then current will be updated to the right by 1 position, just like in guess size. So current, rather than pointing to here, is going to point to right here. So that part there is really the first iteration. Okay, so I can try to actually show to you right here. You can think about this setup. It's really the first iteration. So after the first iteration, you can see current is pointing to this node, but the tau is pointing to this node. So current is 1 node ahead of the tau. So far so good? Okay, let's try one more. Okay. And we go for another iteration. Current is right now mark, which is not null. So we go for another iteration. So we go for, let's say, these 2 lines over here. So tau is going to be assigned to current. So tau, rather than pointing to here, is going to point to the current, which is mark, right here. And the current is going to be moved to 1 position to the right, which is right here. So this will be what's going to happen after the second iteration. Okay. So think about this particular setup is for the second iteration. After the second iteration, the current is still 1 node ahead of the tau. Okay, we're almost getting there. You can think about as soon as the current becomes null, that means it's actually 1 position off the maximum index. In that way, the tau will be just pointing to the right position. Right? Okay, final one. We are just going to check, okay, this condition here. So let me use, how about pink? Okay. So now for the third iteration, you can see the current is actually pointing to Tom. And Tom is not equal to null. So we're going to execute these 2 lines. Again, right? This might be the final time. So tau will be equal to current. So tau, rather than pointing to here, is now going to point to the current, which is Tom, which is exactly the actual tau. At the same time, current is going to be moved from here to its next, which is null. So think about this null over here is more like a position 3, conceptually. Position 3 is exactly 1 off the maximum index, which is 2, right? So this part over here is the final iteration, okay? Third iteration. All right, so after this is done, we know that at this point here, it's really pointing to this particular node right here. So if you go back and check this while loop condition one more time, the current is equal to null. Null not equal to null, false. Exit from the loop. And then just return the tau, which is exactly the last node. So the most important insight when you try to study this example here is to convince yourself the reference for the current is exactly 1 node ahead of the tau reference. That's something like there's a lag behind, right? Think about it. Questions about this? Yes, please.
Will it help the runtime if we, instead of every time setting tail as current, just say if like it's not equal to null, then?
Are you more suggesting maybe adding some if condition here? It might maybe work for some boundary case. Mm-hmm. Huh? Insight?
Because every time you're saying that tail equals to current, right? So instead we just say if the condition of the while loop becomes false, then we say.
It may not be actually necessary. I tell you why, intuitively, right? Because we're really relying on a single Boolean condition to tell us when should we actually stop checking. Because as soon as, let's say, after this particular last iteration, we'll go back and check the same Boolean condition the fourth time. And as soon as that one becomes false, we know, logically, this tail here is now ready to be returned. So there's no need to actually add some extra if check. It might still make the code still working, maybe. Maybe you can give it a try. Otherwise, I think keeping things a bit simpler might be the better. But if you want to continue with the discussion, we can do that maybe after class. Okay, good. All right. All right, quickly, runtime, and then we'll take a short break, right? We are now just about halfway through. Okay. So you want to think about basically the number of iterations. So we are really, again, this will be about, so the number of next reference lookup. That's going to be the dominating factor. Okay? It's going to correspond to how many times we're actually going to run the loop. Right? So that'll be exactly corresponding to the size of the list. Big O of n. Okay? Also linear time. So getting the size and also getting the tail will involve to go all the way to the end of the list by using the next reference lookup. Okay? Of course, as your fellow student pointed out earlier, these two methods, yes, they're linear time. If you really want to, well, if somehow the tail and the size are called so frequently, it may not be worth having these two methods just right here. There might be a better way to do it. Okay, we'll talk about it after the break. Okay, so let's now pause and take a short break. Alrighty. So before the break, we spoke about how you can implement loops for getting the size or getting the tail for the linked list. But again, back to your credit to your fellow student who already spotted that such inefficiency may not be worthwhile. Okay, let's see some scenario. It might be that, so here it's really a matter of how frequently you expect your application to call these methods, like a get size and get tail. If you have to use these two methods so frequently, you don't want to really have linear time algorithm running always. Okay? Let's say, for example, if you have a surface queue, it's like a linked list, and you always want to get to the end of the queue to join somebody. Right? If I just come late, I want to join the queue to the end. That's one way. Right? You want to get to the tail. Or maybe you want to know if the current queue is actually full, in which case you should really notify the customer waiting, things like that, right? So in these cases where size and tail are used so frequently, in this case, we don't really want to call the linear method all the time. So here is one nice little principle you can actually follow. We'll see actually this principle here for a few occasions, but it's more like a software design principle you can actually keep in mind. Maybe later on your 3311, maybe you're taking it or taking later, your instructor might mention this principle, trading space for time. Okay? It's more about algorithm, really. All right, so trading the space for time. Okay, what does that mean? We're going to sacrifice some space, which is okay. Memory is pretty much unbounded for us. We're going to waste some memory space, but at the same time, we can make these two methods, get size and get tail, from linear down to constant. All right, let's see exactly how this will work. Right, just let's sketch the idea a bit. Okay. Again, we have this example list over here that we went through using the methods before the break. First of all, let's see what this principle really means. It's a very useful principle, actually. Very often, whenever you want to define some data structure for your application, right, always think about, for this particular function, do I want to make it an attribute or do I want to make it a method? Okay, there's always some trade-off you have to think about. So trading space for time means we can waste more memory space to make the subsequent computations more efficient. Okay, so we are really trading the space, which is about memory, and also for time, which is about the efficiency for the method. Okay, so in this case, what we will do is we will try to extend the object structure for syncly linked list. Rather than having, just a head, we're going to have 2 more attributes. So that's the assumption we're going to make from now on, right? We got actually 3 attributes in the syncly linked list. Let's talk about the advantages. And then there's also a catch you want to be aware as well, right? So we're going to have basically two more attributes. Let's say we got a tail, and also we got a size. In this case, the tail is actually going to point to the last node right here. And the size is going to store the value 3. Let's assume magically somehow they have been set up there already, right? Magically. But we'll talk about how to really make them work. But for now, let's say it's already there. So let's see what the little extension we have to make. So now in the syncly linked list class, so what we have is we got 3 attributes. We got head, we got tail, and we got size. Okay, so these are all attributes. So these are attributes. Of course, you will incur more cost on space, which is typically not a concern, really. Wasting more space is fine if that can save you time. And let's imagine this. If I try to initialize an empty list, new syncly linked list. If I start with that, I might do a series of, let's say, insertion, removal, whatever, right? That's something we'll talk about. If not today, definitely on Tuesday, right? Just imagine, we somehow manipulate the list in various ways, insert, delete, etc. And now, if suddenly I try to do list dot tail, and also get tail, to be more precise. Get tail. And also list dot get size. Let's say at the moment the list looks exactly like that. So now what will be the cost right now for us to implement the size and tail? Just constant, because I can simply implement this method here. Simply I can say just return the tail attributes. And for this one here, similarly, I can just return whatever value it is for the size. Do you see, can you anticipate, wow, there's no silver bullet. That's what, even though we are trading space for time, it doesn't really mean that it doesn't come with a price. Can you, any one of you kind of imagine what could be the disadvantage for this approach? The advantage is, for any get size, get tail method, it's now it's now constant time. That's good. But what could be the potential drawback? I'll give you a little bit of hints. The potential drawback has nothing to do with any runtime performance. Now the runtime performance has been improved. That's good. However, there's something might be also equally concerning for you as a software developer. I'll pause for a minute, and then I'll take you. I'll just see if a fellow student want to have more time to think about, right? Go ahead. So say it again, I don't quite catch you.
Maybe we can have less space for more lists. So
More space, you know, space is just a head and tail, right? We don't really need any more. Very good. You know, let's understand the question. The advantage of having tail and size attributes is that what we call get tail and get size is now constant time. But it comes with a price. What's that price?
Maybe when we want to add a series of nodes?
Not quite. You're right, you know, somehow, well, not just adding, also removal as well. but it has nothing to do with really runtime performance anymore, okay? Now here's the answer, right? It's a little bit hard to imagine, I know. Maybe this is the first time you're seeing this principle, but the catch you should really know very well. I'll mention that and then I will write it down. The catch is, for all the other methods that you want to declare or define for syncly linked list, you always have to ask yourself, is this method here going to impact the tail or the size attributes? If they are, you have to update it properly. For example, let's say I want to implement a method for insertion. And if I simply do insertion, but I somehow didn't try to update the size attribute over here, maybe from 3 to 4, then I got wrong value for the size. So here's the catch. If you actually want to introduce more attributes so that you can have a cheaper method, that's okay. But you got to make sure those attributes are updated properly. Otherwise, you can easily have inconsistent result being returned, which is even worse than before, right? I'm going to write it down, okay? So there's a catch. So the catch will be for methods that might impact the head and tail and size attributes implementation need to be extended to account for them. Need to be extended to handle. Okay, that's a catch. Somehow, the complexity of your implementation will increase. Okay, that's a little bit shorter version. The complexity. And when I talk about complexity, I'm not talking about running time. Running time might just remain to be whatever it is. It's just the extra code you have to write. Okay, it's more like a trade-off you have to worry about. Okay, so here's the thing. If the size and tail are called so often, I would say go for it. Because just the additional logic you have to program for other methods is going to be worth it. Because you're drastically lowering down the cost for get tail and get size from linear into constant. On the other hand, if you don't really have to call get size and get tail that often, maybe you should just calculate the loop, right, every time. So it's more like a design decision, right? You can think about this one here is no longer just about data structure, right? It's more about a little bit more about software design, which you have to worry about too. Okay. I think we're going to revisit also this principle again, at least another one time when we talk about tree. We'll get there with me once again. Okay. Questions about this? Good. Okay. Let's now talk about one method right away. So from now on, for many of the methods, I will try to put the question here, always remind us. For the method that we want to implement, is it going to impact the size, tail, or head? Always got to keep in mind. If it is going to, you got to make sure your code properly addresses that. All right? So let's now talk about the next method, which will be add first, which is an interesting method. Okay? So we want to insert to the front, which is something we kind of visually did on Tuesday. Okay? We want to insert, given that we are storing string values in each node, so now we want to insert a new node as a first node. That's what we want to do. All right. Okay, this is a Java code. Actually, Java code itself is incredibly simple. Just a few lines. All right. But let's now see how we can understand it. I think that's more important. Okay. Let's take a look. So what we do is, first of all, we are trying to create a new syncly linked list. By the way, this is the implementation for add first. And this is some JUnit test. I haven't really done that yet, but I will also release all the example code I talk about in the class. It's a Java starter. So you can definitely import it from the lecture side and also try to play with it, right? It can be some extra exercise you can do, okay, for your study. Let's now try to see how we can trace this. And just to start with, if you look at add first method here, right? So let's say, for example, if I currently have this list over here, if I want to add a first node, which we learned earlier visually, let's say this will be the first node I want to add, right? So somehow I want to add it before this node here. Now question, is it going to change the head? Obviously, right? Yeah, because the head right now should really pointing to here rather than this node. So head, yes. How about tail? In this example, no. What if the current list is actually empty? What if the current list is such that the head and tail simply point to null? Nothing there. But now if I want to insert first, both of them should be set to that new node. Agree? Not this example here precisely. I'm just saying there might be some boundary case. So potentially, head and tail can be modified. How about size? For sure, should be incremented by 1, right? So all these three attributes should be updated properly. So that's the cost that will come whenever you want, because we have already decided to trade the space for time. Okay, just keep that in mind. Okay, let's now take a look at this. Okay, you'll see that we definitely going to create a new head, some new node over here. That's something we'll trace together with you. Once you get a new node, and now you want to see if the current list has no nodes in there. So now the new node is going to become both the head and the tail. So the tail will only change under this kind of special case. So if you didn't really have this special case here, things will go wrong in the subsequent manipulation. And then also you got to update the size. Okay, so the size, head, and tail, they'll all change potentially. Okay, let's now trace it, and we'll see. Let's now trace carefully for the JUnit test. So let's start with this line. So here we are just creating a new syncly linked list. Okay, that one there, we just visualize it. So we got list, which is pointing to right here a syncly linked list objects. Syncly linked list objects, and we got three attributes. We got a head, we got a tail, and we got a size. I'll put a head over here, and I'll put tail here. And also we got a size. In the beginning, you can think head pointing to null. The tail also pointing to null. The size is equal to 0. Every call to add first should somehow update all these three attributes accordingly, if applicable. Okay. Let's now trace very carefully. And of course, if you try these two assertions over here, get size, 0. Get first, which will be just a head, no. Right? So far, so good. What we'll do is we'll now try to trace these three lines. At first, just see the big picture. Adding first will be Tom. So that means Tom should be now the only node where the head and tail pointing to it. And then when we try to add first Mark, what does that mean? Mark should now come before Tom, in which case head should be pointing to Mark, right? And then another add first Alan. That means Alan is going to be a new node, and now tail doesn't change anymore. But the head should now point to over here. And then, of course, they should be interconnected somehow as well, right? That's something you can expect to see, right, conceptually. Let's now trace very carefully, faithfully, about the lines. The first one, this one here. Okay, at first, Tom. Okay. What that would do is, we're going to, first of all, we're going to this line here. What that would do is, this expression here is going to be evaluated first, before we assign it to head. That one there is going to create a new node, which I'll put here. Okay, so this will be a new node over here. And every node has elements and also the next. All right, so now be careful here. The E here is simply just the element, right? And the head over here is the current head, which is pointing to null. That means it's going to set the element to be Tom. And the next will just be null. That's the green part, right? Just about the new node. And then we're going to assign the head to be there. I'll pause. That single line there is trying to create a new node and set the head to be that new node. Are we okay with it? Okay. And then let's move on. If the current size is equal to 0, it is, because you can see current size here is 0. We're going to set the tail to be the head as well. So that means the tail is also going to point to this node. So this is the special case where you're going to modify both the head and tail. You always have to update the head, but for the tail, only when currently the list is simply empty. Okay, important. Okay, so after this, we're going to also increment the size from 0 to 1. If you somehow feel comfortable about this, I think just 2 more, right? But let's finish that. Okay. So after this, let's now move on to the second line, at first. Right? If you're already kind of following the notes in the drawing, you can kind of think to yourself, how exactly can you draw that, right? But to trace, you got to follow faithfully. So what we do is, again, we're going to execute line number 2 over here. That one there, we're just going to, first of all, create a new node right here. So this will be a new node object here. We got elements and we got the next. Element here would be simple. You just mark. Okay. I can write better. But what about a head? Where should it point to? For the diagram? What should be the next for mark? If you think about the head right here, at the moment, it's really pointing to Tom. Right? This reference. And we're saying that when you create this new node here, whatever head is pointing to, we're going to set the next reference to it. That's what we're saying. Okay, that part there, make sure you're okay, but if no, you should really approach me as soon as you can. So important, all right? So what I will do is, now the next is going to point to exactly here. And right now, size is actually 1. Equals 0, false. So we don't really try to set the tail anymore. Skip that. And then we're going to increment the size from 1 to 2. The next step will be just identical to this one here. But before that, let me emphasize again, it is so important for you to really see why this new node creation over here, right here, is going to set the next to be the current head, which is Tom, right here. That's so important to get right. All right? All right, let's do one more, and then I can say something more. Let's now do the third node at first as well. That one there is going to be identical to what we just did. So what we do is, this line here, we're going to create a new node. Which will be right here. New node, we got element, we got next. And element here will just be Alan. And then the head over here right now, you can see is, oh, back up did I set something? Oh, there's something I forgot, actually. I beg your pardon, my apology. Okay, I just forgot. I said that, but I forgot to actually update the diagram. Let's wind back a little bit, okay? When I was talking about this line over here, right? We spoke about when you create this new node, we're going to set the reference over here. What I missed was you should set the reference of this new node to be the new head. That's something I forgot, okay? Again, my apology. You should really make sure you include it, okay? So what that one will do is it's going to say head, rather than pointing to here, it's going to point to whatever new node we have created, the blue node, which will be right here. All right. Okay, I just missed that. Okay. So now if we go to the third one here, Alan, okay, we have created Alan here, and then the next should be the current head. And the current head is actually Alan, sorry, Mark, right here. So what that will do is the next will be pointing to wherever Mark or the head is pointing to. That's what you will do. All right. And then, of course, this time I'll remember. Once you have got this node here, you want to make sure this node reference is assigned to the head to update it. Okay. So the head, rather than pointing to Mark, is now going to point to just this node right here. And we go to evaluate the if condition here. Size is now 2, not equal to 0. So we skip this part here. And then we try to increment the size from 2 to 3. That's the final outcome. Let's try to highlight to see everything. Okay. So what we have is now this structure. So what we have is we got this syncly linked list at the top level. Okay, let me just, we got this syncly linked list at the top level here. The head is pointing to this node. And the tail is pointing to this node right here. And somehow these nodes are interconnected, like that. So it's being set properly. Okay. Questions about this? Go ahead.
So for the second line, I think when I first started, it wasn't very intuitive. Would it have been like valid if I made a temp equals new node head and then I set head equals temp?
Oh, you mean to kind of use maybe more than one line to set it, right? Yeah, no problem. Why don't we do it? I think it's valid, right? No problem. The runtime will be just the same. It will still remain to be constant. Okay, let's do it. Let's now try to rewrite these lines. Okay, there's an alternative. Okay, okay, let me say star. Okay, what I can do is, first of all, I can say node, new node, NN will be new, and then node, whatever element it is, let's say null for now. Okay, first line. After that, I can say new node dot set next should be the current head. Think about these two lines right here just correspond to this part over here. And then after that, we're just going to do one more, which is going to say the head is assigned to the new node. Okay? So we are saying that these three lines, these three statements here, correspond to this one line. Okay? That's good. I'm so glad they actually mentioned that. That's great. Guys, you can either go for the one-line version, but you might find the three-line version a little bit more intuitive, which is completely okay. But I would say just get used to both. Okay. What's the running time? Constant, right? There's no loop, right? It's obvious, right? So I would say even without knowing exactly what these variables really mean, just based on what we learned from the asymptotic lecture, so this will be constant time, right? Only variable assignments. So the running time is big O of 1. All right? All good? Any questions? Okay, I think we've got 7 minutes. We can definitely move on a little bit further. Okay. So on the slides, I actually mentioned about two possible, okay, let's insert to the front, two possible exercises about remove first and also add last. So these are the two methods I will encourage you to really download the code I'm going to make available on the lecture site and try to implement in Java. But I'm going to help you a bit. That'll be it for today. Okay? I'm just going to give you some visual hints about what you should really do. That's pretty much what you have to do already. Right? Let's do it quickly. So let's see how we can remove the first node and how we can add a last node, meaning that we're going to create a new node. Okay? Okay, hints. Now that you're going to give you got to give some precise implementation. You have to really look for boundary cases. Right? For example, when we try to add the first, when the size is equal to 0, we're going to change the tail as well. It's more like a boundary case. It's like only certain condition will actually make it happen. Right? Let's say if I want to remove the first, the boundary case would be, what if the list is empty? Does it have the first element for you to remove? Not really. Right? So in that case, it should be like an exception. Right? You can create some exception like what you did in 2030 and throw it. So boundary case will be when the size is equal to 0. You can just check the size, right? The attributes. And how does it look like? So in this case, for remove, so you got SLL over here. So you got a head. Also, you got a tail. Also, you got a size, right? When the size is equal to 0, we know that the head and tail simply pointing to null. So this is not a valid situation for you to remove something. You just cannot remove from the empty list. So this should be some exception. On the other hand, in the case of, let's say, adding a first node, so this is like a remove. How about adding a last node? In that way, you actually don't really have to worry about throwing exception. You can add as many as you like, right? But this one is slightly different. Let me sketch that, okay? So now if you want to add a last node, let's say we start with boundary case will still be size equal to 0, but we're going to handle that a little bit differently, okay? So let's say we got our singly linked list just as before. And then we got the head. And we got the tail. And we got the size. Size will be 0. And the head and the tail will just be null. We definitely can add a last node for sure, right? But how do we update? Very similar to add first, actually, very similar. So let's say if we are trying to store value e here. So what we do is we create a new node right here. And then the node has elements and also next right here. So the element is going to point to wherever e is pointing to, basically, right? Just some elements. And then the next will just be null. Let's say, well, once we create a node, we're going to make sure the head has now become a new node. And also the tail also has become a new node. Right? So now you can think about in empty case, in the add last node, and also in the remove first node, they have to be handled differently. Okay, that's the main point. Okay? But they're same boundary cases, but you're going to handle them differently. Okay, so why don't we do, let me start with removing the first node. Let's see. Another one you can also see very quickly. Okay, just for this one, I forgot to mention. If the current size is equal to 1, only one node, after removing the first node, the list becomes empty. Right? Result will be empty list. Okay. Let me at least give you the hints for removing the first node. I think it'll go about 2 minutes, but we'll see. At least one. Okay. So now what should we do? Let's say here we got a list already, and I want to remove this particular node. Okay. So now the general case is when the size is not 0, it's not 1. It's larger than or equal to 2. You can put like an else condition. I'll leave the implementation detail to you. Right? And we're going to have some step. Okay? I'll just give you some step. Number one, we're going to get the current head right here. Let's call it temp. Okay, this will be step number 1. Just have some reference. And then step number 2. The head over here should be updated to the current second node, because the first one will be removed. So the second step will be the head is the second node. Okay, you can work out what Java line you have to write. Should be easy. Okay, that'll be second step. And the third step will be this node, because it's going to be removed. So his next node, next reference should be set to null, right? Number 3, set to null. And the final step will be, you got to make sure, so currently the size is 3. We want to update it to 2, because you have removed the node. So this will be step number 4. Updates the size. So there are 4 steps in total. We got 1, and then 2, and then 3, and then 4. Okay, give me 1 minute, and then I'll be done. Okay. These are the 4 steps. Pretty much, you can just figure out exactly what the line of Java code to write. I think it's pretty much fixed. But what's the running time? Big of 1, right? There's no loop. Awesome. Good. So it's going to be big of 1, because none of the steps depends on the number of nodes in the list. If it does, we have to use a loop, but we didn't, right? So that's why it's a constant time operation. Okay. So next time, I will maybe give you a little bit quickly some hints about this one here, but you can definitely give it a try. So it'll be very similar to what we talked about on Tuesday. All right, thank you so much. I'll see you next week.